Uh, in this video, we are going to discuss about the mathematics which are related to the cryptography. Basically, in this video, I'm going to discuss about the Chinese remainder theorem, quadratic congruence, as well as the fast exponentiation method. Chinese remainder theorem is used to solve the congruence equations. Quadratic congruence, there are certain relationship which is quadratic in nature. How to solve that quadratic congruence relationship, as well as there are many algorithms which you use to use the exponentiation for the encryption and decryption process. So there must be a certain process, must be algorithm, which are going to discuss how to solve that one, and that is the first exponentiation method. So first of all, going to discuss about the Chinese remainder theorem. Now this theorem is used to solve the set of the congruent equations having one variable but with the different moduli, and those moduli must be the relatively prime. Whenever we talk about moduli, it is the plural of modulus. When we talk about a single equation, congruent equation, that is x is equal to a mod m, m is called modulus. But if there are certain equations which are there are many equations and with the same variable, then how to solve that equation? So there are different modulus, so in combination, in plural, it is called moduli. So this Chinese remainder theorem is used to solve the congruent equation having only one variable. So for example, suppose we have three equations: x is equal to a1 mod m1, x is equal to a2 mod m2, and x is equal to a3 mod m3. So how to solve and how to get the value of x, because a1, a2, a3 are different. The modulus values are also different, m1, m2, m3. So how to solve? So Chinese remainder theorem states that how to solve this equation. So this above equation has a unique solution. The above equation has the unique solution and it can be solved. First of all, the first step is to calculate the capital M, which is nothing but it is the multiplication of all the modulus or all the modulus value. If there are three equations, two equations, four equations, whatever it may be. So M is equal to M1 into M2 into M3, and this is called the common modulus. And then we try to find out M1. With the help of M, we try to find out M1, and that is M1 is equal to M upon small m. M2 is equal to capital M upon small m2, and M3 is equal to capital M upon small m3. So with the help of this, we are able to calculate M1, capital M2, and capital M3. And then what we do, we try to find out the multiplicative inverse of M1, M2, and M3. Uh, and how to find out the multiplicative inverse? We have already discussed with the help of Fermat's theorem. We can find out the multiplicative inverse, that is M1, that is M1 inverse, M2 inverse, M3 inverse, by using a certain formula, and that formula is M1 inverse is equal to M1 P minus 2 mod P, where P is a prime. So, and then after calculating all these three steps, after going to these three steps, then we find out the solution, that is x is equal to a1 m1 m1 inverse plus a2 into m2 into m2 inverse plus a3 into m3 into m3 inverse mod m. And whatever value we will be getting after doing mod m, that will be the value of x. So this Chinese remainder theorem can be better understood by a simple example. Suppose we have an example and simultaneous equation given is x is equal to 2 mod 3, y is equal to 3 mod 5, z is equal to 2 mod 7. Of course, the variable is same, x, y, z is same, that is x, x, x you can consider. One is, the first equation is 2 mod 3, so modulus value is 3. Second equation, modulus value is 5. Third equation, the modulus value is 7. So we adopt the first step to calculate capital M, that is the multiplication, which is called common modulus, which is the multiplication of all modulus, that is 3 into 5 into 7, that is coming around 105. So then the step number 2 says that find out the value of M1. How to get the value of M1? That is capital M divided by small m1. The small m1 is 3, so 105 by 3, that is 35. M2 is calculated 105 divided by M2. M2 is 5, so it is 21. M3 is equal to 10 capital M upon M3. M3 is equal to 7, so it is 50. And then we have to find out the inverse. So first of all, we have to find out the M1 inverse. M1 inverse means 35 inverse with the mod value 3. So how to get 35 inverse mod 3? There is a simple way of the calculating that 35 inverse of mod 3. Now this value is more than modulus value. So first of all, we will try to find out the remainder of 35 when it is divided by 3. So 11 3s are 33, so we will be getting 2. So it is actually 2 inverse mod 3. It means you have to find out the inverse of 2 with modulus value 3, meaning thereby by what value you multiply 2, with what integer you multiply 2, so that whenever you are taking mod 3 it should get 1. So it is 2 only, because if 2 is multiplied by 2 it will be 4, and 4 mod 3 will be 1. So it means the inverse of 2 will be 2. Otherwise you can use the formula, this one, m1 p minus 2 upon m mod p. So if you are applying this, so 2 to the power 3 minus 2, p minus 2, 2 to the power 3 minus 2, that will become 2 to the power 1. So 2 to the power 1 is equal to 2. So the inverse of m1 will be 2. Similarly, inverse of m2 will be 21 inverse mod 5. Again, 21 is more, so we will first uh, take the remainder. 5 4s are 20, so we'll get 1 inverse mod 5. 1 inverse mod 5, 1 inverse, 1 ka inverse, multiplicative inverse of 1 is always 1. Similarly, whenever we are calculating m3 inverse, we are getting again 15 inverse mod 7, again 15, 1 inverse mod 7, and that is calculated as 1. So it means m1 inverse is 2, m2 inverse is 1, m3 inverse is 1. So what we'll do, we'll adopt the last step. That is x is equal to a1 m1 m1 inverse and so on. So 2 into 35 into 2, 3 into 21 into 1, 2 into 15 into 1, mod capital M, that is mod 105. So whenever we are calculating, we are getting 23. So when 23 is obtained, it means 23 is the exact answer. So how, whether this 23 is correct or not, let us check. Let us check if x is equal to 23, and if we are making mod, if we are taking mod 3, 23 mod 3, whether we are getting 2 or not. So 23 mod 3, 3 7s are 21, so we'll get it 2. So it means this is satisfied. 23 mod 5 will be 5 4s of 20, so we'll get it 3. So similarly, 23 mod 7, 2. So it means it is correct. So whatever value in the form of answer we have got, 23, it is correct. The second one is the simultaneous equation, which is given as x is equal to 3 mod 7, y is equal to 3 mod 3, z is equal to 0 mod 12. Now this is not x, y, z. This is 3 different equations, but the same variable is there. X, y, z is same. So again, we will be, this is the second example. So we are calculating m is equal to 1092 as 7 into 13 into 12. m1 is equal to 1092 upon 7 and so on. Then we have to find out the inverse. So 156 inverse mod 7 is actually equal to 156 to the power 5 mod 7 by applying the Fermat's theorem. 156 to the power p minus 2. So 156 p minus 2, 156 mod 5. Since 156 is already more than 7, so why not to divide and find out the remainder? So we get 2 to the power 5, because 156 mod 7 is already 2 to the power 5. And 2 to the power 5 is 32. 32 mod 7, 7 4s are 28. 28, 32 minus 28, that will get 4. Similarly, inverse of m2 is to 84 inverse. 84 inverse, we apply the same Fermat's theorem. 84 p minus 2, p is 13, so 84 11, 84 to the power 11 mod 13. So 84 is already more, so when take the remainder of 84, when it is divided by 13, we will be getting 6. So 6 to the power 11 mod 13, and we will be getting value 11. Similarly, m3 inverse is 91 inverse, and we are getting as 3. Now the step number 4 says we multiply 3, 156, and its multiplicative inverse, and so on. So ultimately we are getting 276. Now 276, whenever it is applied with mod 7, you will be getting remainder 3. 276 applied with mod 13, you will be getting remainder 3. And similarly, 276 mod 12 is already getting 0. So this answer is correct. So this is the way how Chinese remainder theorem can be applied for solving the simultaneous congruence equations. Now, quadratic congruence. Now, it is not necessary that whatever equation we are getting in the form of a simple quadratic congruent equation, but it may be the equation which is having x square congruent to a mod p, where p is a prime and a is an integer, and p does not divide a, and p does not divide a, then only we will have a solution. So this type of, now x square a mod p, and then you have to find out the value of x. So how to get it? So this kind of equation is called quadratic congruence. Now this kind of problem either have no solution or two exactly incongruent solution. This type of equation will have either no solution or it may have two incongruent solution, depending, it depend on that, on the value of a. What is the value of a? What is the status of a? If a is quadratic non-residue, if a is quadratic non-residue, and if a is quadratic residue, if a is quadratic non-residue, then it means it has no solution. But if a is quadratic residue, then it has a solution. Then what is quadratic residue? Let us discuss. If a to the power p minus 1 divided by 2 is equal to 1 mod p, then a is a quadratic residue modulo p. Otherwise, it is, if it is a to the power p minus 1 divided by 2 is minus 1, it means a is a quadratic non-residue. So first of all, while solving this equation, it is necessary to check whether a is a quadratic residue of mod p or not. If it is so, and how to get it? You have to find out a to the power p minus 1 divided by 2. If it is 1, then it is quadratic residue, and if it is minus 1, then it is quadratic non-residue. Now, in the example Z11 star, we have 10 elements, 1 to 10, and it has, now every element is not a quadratic residue. Only 1, 3, 4, 5, 9 is a quadratic residue, and 2, 6, 7, 8, 10 is a quadratic non-residue. Why it is so? Because when we apply 1, 3, 4, 5, 9 on this equation, then only we are getting 1. Otherwise, if we are applying 2, 6, 7, 8, 10, and then a to the power p minus 1 by 2 it is applied, we are getting minus 1. So that is why it has been categorized as 1, 3, 4, 5, 9 is a quadratic residue, because a to the power any value of this set, if it is raised to the power p minus 1 by 2, if since we are getting 1, so that is, it means this is quadratic residue and this is not quadratic residue. So this type of equation will be solved, will have the solution if a is a quadratic residue. Otherwise, if a is not a quadratic residue, then it will not have a solution. So let us give an example. Now, to find out the solution of x square congruent to a mod p, consider the prime number p as p is equal to 4k plus 3, where k is an integer. So if p is prime and a is a quadratic residue in zp, then x will be equal to 8. Now, what will be the solution? Solution will be, agar a is a quadratic residue, if a is a quadratic residue and p is a prime number, then this equation will have two solutions. The first solution will be a to the power p plus 1 divided by 4 mod p, and the second solution will be minus a to the power p plus 1 by 4 mod p. Now, suppose this is the equation, x square congruent to 3 mod 23. So we have to find out the solution. So to find out the solution, it is necessary to check whether 3 is a quadratic residue in mod 23 or not. So let us check. Since 3 is, now it is already assumed that 3 is a quadratic residue. So if 3 is a quadratic residue, then it will have two solutions. The first solution will be x square is equal to 3 to the power p plus 1. P is 23, p plus 1 divided by 4, that is 3 to the power 6 mod 23, and we are getting 16. So it means under root 3 will have two solutions, plus minus 16 mod 23. Another example, x square congruent to 2 mod 11. If 2 is a quadratic residue, then it will have solution. Since 2 is not a quadratic residue, so it is not having no solution. Since second example is x square congruent to 7 mod 19. Since 7 is a quadratic residue, so for checking that whether it is quadratic residue or not, you have to use this formula. And since 7 is a quadratic residue, so solution will be x will be equal to x to 7 to the power 19 plus 1 divided by 4 mod 19, which is 7 to the power 4 mod 19, that is 49 mod 19, that is 11 mod 19. So under root 7, meaning there the value of x will be plus minus 11 mod 19. So this is how the quadratic congruence are being solved. Now, the previous equations have that this p is a prime number. But if there is a congruent equation where p is not a prime number, if p is a composite number, for example, it is 77, then how to obtain the value, how to obtain the solution. So, suppose the example is x square congruent to 36 mod 77, and 77 is not a prime number. So, 77 is 11 into 7. So 77 is 11 into 7. So this equation can be divided into two parts. First part will be x square congruent to 36 mod 7, and that will be 1 mod 7, and x square is equal to 36 mod 11, and it will be equal to 3 mod 7. So it means we have two equations now. One is x square is equal to 1 mod 7, and second equation will be x square is equal to 3 mod 7. Actually, it is not 7, it is 11. So the solution will be x will be a to the power p plus 1 by 4 mod p, that is 1 cube mod 7, that is plus minus 1 mod 7, and another will be a to the power p plus 1, that is 3 to the power 3 mod 11, that is plus minus 5 mod 11. So we have four solutions. The first solution is plus 1 mod 7 plus 5 mod 11 plus 1 mod 7 plus 1 mod 7 plus minus 1 mod. So we have using these are the solutions. So we have now four equations, and with the help of Chinese remainder theorem, we have to solve these equations to find out the value of x, that is plus minus 6 or plus minus 27. So first case, we have to select x is equal to 1 mod 7 and x is equal to 5 mod 11, and then we have to apply Chinese remainder theorem to get the solution of x. Next time we have to consider x is equal to plus 1 mod 7, and another will be minus 5 mod 11. Then you have to find out the new value of x. Similarly, x is equal to minus 1 mod 7 and x is equal to plus 5 mod 11. Then we have to get the value of x by using Chinese remainder theorem. And ultimately, whatever result we will getting, that is x is equal to plus minus 6 and plus minus 27. So it has four solutions. Now, exponentiation and the logarithm. Now, exponentiation, a to the power x, logarithm is the inverse of that. So exponentiation and logarithm are counterpart of each other. Exponentiation can be represented in the form of y is equal to a to the power x, and logarithm is nothing but x is equal to log to the base a, log y to the base a. So in cryptography, in most of the cases, algorithm which is being applied, it uses exponentiation process. That is y is equal to a to the power x mod n. You have seen the Diffie-Hellman key exchange in which this kind of algorithm is being used, this type of equation is being used. And in asymmetric cryptography, you will be using RSA crypto system, where the exponentiation is used both in the encryption as well as decryption, and not the exponentiation, not of the smaller exponent, but the larger exponent. So we are in need of the calculation of this kind of exponentiation, and we need an algorithm, we need a method by which we can efficiently able to calculate. If x is equal to too large, then how this large value of x will be able to calculate the value of y. Because if x value is 2, then a square mod n. If x is equal to 4, then a to the power 4. But if x is equal to 1004, then it seems to be very difficult, because normally, conventionally, the exponentiation method is used by multiplication only. If it is a square, it means a into a. If it is a to the power 4, it is a into a into a into a. If it is a to the power 104, then it means a multiplied by 104 times. So it is not very efficient process. So we are going to discuss now the efficient algorithm which is used for the calculation of such kind of things. The exponentiation can be calculated with the help of a fast exponentiation method, and traditionally we use only multiplication to simulate the exponent, but This fast exponentiation method uses square method as well as multiply both, besides only using the multiplication. So how it is being done? If suppose y is equal to a to the power x mod n, and the value of exponentiation is first converted into a binary number. Suppose the example is y is equal to a to the power n mod 9. So what we will do? We change the convert this decimal value into a binary value. So binary value is this one. So this actually means what? A to the power 8 into 1, a to the power 0, a to the power 0 into a to the power 1 mod n. So this is the prerequisites of fast exponentiation. Now fast exponentiation says that y is equal to a to the power value. Now which value? Which is a polynomial equation. Now x to the power nb minus 1 into 2 to the power nb minus 1 plus x to the power x subscript nb minus 2, 2 to the power nb minus 2, and so on. So y will be, the value is calculated as a to the power n, a to the power 2 n b minus 1 or 1, a to the power n b minus 2 or 1, or a square or 1, or a like that. So example is very simple, which has been illustrated in the last slide. That y is equal to a to the power n, it will be converted into 1001. It means a to the power 8 into 1 into 1 into a. So this is the algorithm, and the algorithm says that you have to know, you have y is equal to a to the power x mod n. So you must know the value of a, you must know the value of x, and you must know the value of n. All these three are known, and you have to find out y. So we first calculate y is equal to 1. We initialize the y is equal to 1, and then what we do, from I is equal to 0 to nb minus 1, where nb is the number of bits in x. Number of bits in x. Why number of bits? Because if we have seen the example, if it is y is equal to a to the power n, there are 4 bits. So how many times? It will be this iteration process, the I value will be from 0 to 3 in this particular case, if number of bits are 4. So the first, when the I is equal to 0, what will happen? We will check whether x0 is equal to 1 or not. If x0 is equal to 1, then y is multiplied. Then y will become a into y mod n. Y is initialized as 1. A we already know, so we can find out the new value of y. But if x0 is not 1, we will skip this method. So that is why it has been written that multiply only if the bit is 1. If the bit is 0, then we will not multiply. And then a is equal to a square mod n. New value of a is updated. Y is updated here, and the new value of a is updated. By what? Squaring is not needed in the last iteration, but squaring is done after every aspects. Now, y will be updated only if the bit value is 1. Otherwise, y will remain the previous value. And a will be updated every time, besides the last iteration. And after all, after this execution is over, if iteration is over, whatever is the value of y, that is considered as y, the solution. So this is how it used to work. But let us check that how a to the power 22 using a square and multiply method or the fast exponentiation method is used. Now, you know, when we convert 22 into binary number, it will become 1 0 1 1 0. So when this x0 is 0, y remains as it is, no change in y. But when y is equal to, when x0 is equal to 1, we multiply, and when we multiply, we will taking y is equal to a square. And then since x2 is equal to 1, then we multiply, y is equal to a to the power 6. Now this value is 0, so we will not multiply, and we will go. Now this C, the multiplication is being done if the bits are 1. Whenever bits are 0, it is passed as it is. And here again it is 1, so it is being multiplied. So we are getting a to the power 22. How it is being done? Let us take an example that how to calculate the value of 17 to the power 22 mod 21. So 22 has been 0, 1, 1, 0, 1. This is the least bit, and this is the most significant bit. So since the least bit is 0, so we don't do any multiplication, we directly do the squaring. So a will be equal to 17 square mod 21, that is equal to 60. Now the next iteration, the xi value is 1, so we will do multiplication. We will do multiplication of what? Y is equal to a into y mod 21. So previous value of y is 1 and the new value of a is 16, so 16 into 1, that is equal to 60. And again we will do the squaring method. Squaring a is equal to 16 square mod 21, that is equal to 4. Now the third iteration, x is again 1. So we will do the multiplication. Multiplication of what? Previous value of y, that is 16, new value of a, that is 4, and then mod 21, that is coming 1. Again, squaring is being done. A is equal to 4 square mod 21, that is equal to 16. Now the next iteration, the xi bit is 0. So we'll don't do any multiplication, but we do the squaring, that is equal to 4. And in the last iteration, y is changed, updated by previous value of y, that is 1, new value of a, that is 4, and that is equal to 4. So 17 to the power 22 mod 21 is equal to 4. And in the last iteration, it has been mentioned in the algorithm that we don't do any squaring. So we will adopt as many as steps as it can be, and it depends upon the number of bits. So that is how the square multiply method is being used. It is also called the fast exponentiation method.